Describe the domain of f of x equals 2 times the square root of the quantity x plus 3. The radicand cannot be negative, so x plus 3 is greater than or equal to 0, which can be represented by the inequality x plus 3 greater than or equal to 0. Subtracting 3 from each side of the inequality gives x is greater than or equal to negative 3. So the domain is the set of real numbers greater than or equal to negative 3. Graph f of x equals the square root of x plus 4. Describe the range of the function. First find the domain of f. Because the radicand cannot be negative, the domain of f is x greater than or equal to 0. Use the domain of f to make a table of values. Substituting 0 for x in the function f gives f of x equals 4. Similarly, when x equals 1, f of x equals 5. When x equals 4, f of x equals 6. When x equals 9, f of x equals 7. And when x equals 16, f of x equals 8. So to graph the function, plot the ordered pairs 0, 4, 1, 5, 4, 6, 9, 7, and 16, 8. Then draw a smooth curve through the points starting at 0, 4. From the graph, you can see that the range of f is y greater than or equal to 4. Graph g of x equals negative the square root of x plus 2. Compare the graph to the graph of f of x equals the square root of x. Begin with the graph of f of x equals the square root of x. Then find the domain of g. Because the radicand cannot be negative, the domain of g is x greater than or equal to 0. Use the domain of g to make a table of values. Substituting 0 for x in the function g gives g of x equals 2. Similarly, when x equals 1, g of x equals 1. When x equals 2, g of x is approximately 6/10. When x equals 3, g of x is approximately 3/10. And when x equals 4, g of x equals 0. So to graph g, plot the ordered pairs 0, 2, 1, 1, 2, 6/10, 3, 3/10, and 4, 0. Then draw a smooth curve through the points starting at 0, 2. The graph of g is a reflection in the x-axis and a translation 2 units up of the graph of f. Let g of x equal 3 times the square root of the quantity x plus 1 minus 3. Part A. Describe the transformations from the graph of f of x equals the square root of x to the graph of g. Step 1. Translate the graph of f horizontally 1 unit left to get the graph of t of x equals the square root of the quantity x plus 1. Step 2. Stretch the graph of t vertically by a factor of 3 to get the graph of h of x equals 3 times the square root of the quantity x plus 1. Step 3. Translate the graph of h vertically 3 units down to get the graph of g of x equals 3 times the square root of the quantity x plus 1 minus 3. Part B. Graph g. To graph g, first find the domain of g. Because the radicand cannot be negative, x plus 1 is greater than or equal to 0. Subtracting 1 from each side of the inequality gives x greater than or equal to negative 1. Use the domain to make a table of values. Substituting negative 1 for x in the function g gives g of x equals negative 3. Similarly, when x equals 0, g of x equals 0. When x equals 3, g of x equals 3. And when x equals 8, g of x equals 6. So to graph g, plot the ordered pairs negative 1, negative 3, 0, 0, 3, 3, and 8, 6. Then start at the point hk, or negative 1, negative 3, and draw a smooth curve through the points. The model v of d equals the square root of the quantity 2 times g times d represents the velocity v in meters per second of a free-falling object on the moon, where g is the constant 1 6/10 meters per second squared, and d is the distance in meters the object has fallen. The velocity of a free-falling object on Earth is shown in the graph. Compare the velocities by finding and interpreting their average rates of change over the interval d equals 10 to d equals 20. Use points whose d coordinates are 10 and 20. First find the average rate of change on Earth. Use the graph to estimate the points whose d coordinates are 10 and 20. Using the graph, notice that when d equals 10, v is approximately 14, and when d equals 20, v is approximately 20. So use the points 10, 14, and 20, 20. The average rate of change of the velocity of a free-falling object on Earth is given by the quantity v of 20 minus v of 10 divided by the quantity 20 minus 10. Substituting 20 for v of 20 and 14 for v of 10 simplifies the expression to the quantity 20 minus 14 divided by 10, or 6 divided by 10, which equals 6/10. Next, find the average rate of change on the moon. To find the average rate of change on the moon, use the function v of d equals the square root of the quantity 2 times g times d, and evaluate v when d equals 10 and d equals 20. Substituting 10 for d and 1 6/10 for g gives v of 10 equals the square root of the quantity 2 times 1 6/10 times 10, which simplifies to the square root of 32, or approximately 5 7/10. Substituting 20 for d and 1 6/10 for g gives v of 20 equals the square root of the quantity 2 times 1 6/10 times 20, which equals the square root of 64, or 8. So use the points 10 the square root of 32 and 28. The average rate of change of the velocity of a free-falling object on the moon is given by the quantity v of 20 minus v of 10 divided by the quantity 20 minus 10. Substituting 8 for v of 20 and the square root of 32 for v of 10 simplifies the expression to the quantity 8 minus the square root of 32 divided by 10, or approximately 23 hundredths. So from 10 to 20 meters, the velocity of a falling object increases at an average rate of about 60 hundredths meters per second per meter on Earth, and about 23 hundredths meters per second per meter on the moon. The distance d in miles that you can see to the horizon can be modeled by d of x equals the square root of the quantity 3x divided by 2, where x is the height of your eye level in feet above the ground. Part A. Use a graphing calculator to graph the function. At what eye level height does the distance you can see to the horizon exceed 6 miles? To find the eye level height at which the distance you can see to the horizon exceeds 6 miles, find the value of x when d of x is about 6. First enter the function into your calculator and graph it. Then use the trace feature to find the value of x when d of x is about 6. So the distance exceeds 6 miles at an eye level height of about 24 feet. Part B. What happens to the average rate of change of the distance as your eye level height increases? Compare the average rates of change over several intervals. The average rate of change over the interval x equals 0 to x equals 20 is given by the quantity d of 20 minus d of 0 divided by the quantity 20 minus 0. Evaluating d of 20 and d of 0 gives the quantity the square root of 30 minus 0 divided by 20, which simplifies to approximately 274 thousandths. The average rate of change over the interval x equals 20 to x equals 40 is given by the quantity d of 40 minus d of 20 divided by the quantity 40 minus 20. Evaluating d of 40 and d of 20 gives the quantity the square root of 60 minus the square root of 30 divided by 20, which is approximately 113 thousandths. The average rate of change over the interval x equals 40 to x equals 60 is given by the quantity d of 60 minus d of 40 divided by the quantity 60 minus 40. Evaluating d of 60 and d of 40 gives the quantity the square root of 90 minus the square root of 60 divided by 20, which is approximately 87 thousandths. So the average rate of change of the distance decreases as your eye level height increases.